Bonjour. So welcome back to QX01, Introduction to Quantum Information and its Associated Technologies. So let's have a look at what we covered so far. So we've seen the introduction of the subject. We've seen a reminder of classical information and computation. And we've covered perhaps the basic element, the quantum bit, the qubits, and we started last week to talk about multiple qubits. So we're going to finish that today and discuss also the notion of entanglement. So in this part, so some aspects that we've covered already. So definition of a multiple qubit. So I'll come back to that quickly. We started to define the notion of tensor product that we said we would need. And then today we will carry on by the notion of Hilbert space and parallelism that we talked about already. So we will see how the parallelism comes in here. And then the very important notion of entanglement between two qubits or between two particles. And then we'll discuss one example of how we can make 2, 3, and 4 qubit states in practice or more, and by using what's called path encoding for photons. And then to finish that, I'll come back to what I said, some aspects of the physical meaning of psi, the so-called wave function of the system. As I said, I will have to come back to the physical meaning to it, to understand a bit better what's behind. Right. So we said that we've covered so far the notion of column vector, row line vector, and the bracket notation with the bra and the ket vectors and the dual space, dual vectors. We talked about the inner product. We defined it, which can be seen as a scalar product. We covered Hermitian matrices and the product of matrices, although we'll come back to that in the next lecture. And then two more notions are left that we will see in that chapter. So the first one is tensor product that we already started. And the second one is the outer product. We've seen the inner product, and now we're going to see also the outer product. So as a reminder, multiple qubits means several qubits. So the first and the first easiest multiple qubits is 2 qubits. So what does it look like? So here is the 2 qubit state, the most general 2 qubit state you can have between 2 qubits. So each of them can have, of course, the 0 or 1 output. So put them together, you have the 4 output that you would have with two bits of information, 0, 0, 0, 1, 1, 0, and 1, 1. Now, as we're dealing with quantum technologies, we have the quantumness of it, which is to have all these possibilities in one go in a superposition state of all these 4 possibilities, with coefficients alpha 0, 0, alpha 0, 1, alpha 1, 0, and alpha 1, 1. With the same rules as before, is that these coefficients are complex, and we like to use normalized to 1 vectors as well, or qubits. But so what we can see here is that this 2 qubit state, this 2 qubit system, is actually a 4-dimensional vector, right, with 4 coefficients. So as said before, so using 2 qubits, we went from a 2D vector to now a 4D vector. Okay, and so as a reminder, we can write this vector in a sort of normalized notation: 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0. Okay, the equivalent of what we had before, where it was just 1, 0, and 0, 1. So that's for 2 qubits. So if we have a look at 3 qubits, then what we get now is an 8-dimensional vector. Again, the idea of having 2 to the power of n, where n is the number of qubits. So that's now the space that 3 qubits would live in, where you have 8 coefficients and all the 8 possibilities in a superposition state going from 0, 0, 0 to 1, 1, 1. Okay? And for n qubits, we are going to have 2 to the power of n vector. So if we want to give it a name, or this future quantum computer, this parallellator or superposator will increase exponentially the number of components that we have as a function of n. So just a reminder as well, one notation we said is that 0, 0, 0. So this is one notation, but we could write it like this. Okay, so it's the same thing. It's the sort of product of the 3. And sometimes you will also see a notation where you actually have an index to say this is qubit 1, qubit 2, qubit 3. Or also, this notation sometimes occurs, or you could have another result, which is, for instance, 1, 0, 0, 0. Okay? So that would be qubit 1, qubit 2, qubit 3. Right. So what we saw is that, so going from 1 qubit, we have a 2D vector to a 2 qubits, we have a 4D vector. So mathematically, we need something. We need an operator. We need an operation that allows us to go from a 2-dimensional space to a 4-dimensional space, or 8-dimensional space, and so on and so forth. And there is one operation in math, is the so-called tensor product that we usually write as a circle with an x in the middle. And so if I take the tensor product between these 2 qubits, so the equivalent of qubit 1 or qubit 2, so psi, so phi and psi, then if I want to put these 2 qubits together, then I have to use the tensor product operation in order to, at the end, get a 4-dimensional vector. So how do I do this? So I start from the 2 qubits. So I tensor product them together. And so I define the first one as being alpha 0, alpha 1, tensor product, beta 0, beta 1. And how do we do this? The idea is that so we have a 4D vector. And what we do is we take the first one and sort of multiply it to the second vector together. And then we take the second one and multiply it to the second vector. So we will have alpha 0 of beta 0, beta 1. And we would have alpha 1 of beta 0, beta 1. And that would give us 4 components. So alpha 0, beta 0, alpha 0, beta 1, alpha 1, beta 0, and alpha 1, beta 1. Okay? Right. So this is it. And the thing is, the tensor product, or another way of seeing it, is it can be seen also as an actual multiplication between the 2 qubits. Because if I multiply phi and psi, I would, so if I develop the expression, I would have 4 terms, which is this term, this one, and this one. And if I use up the, so if I define the coefficient, redefine the coefficients as being alpha 0, 0 equals alpha 0, beta 0, and so on. And also, if I use a notation so where I combine the two qubits together, then I end up with the definition of a two-qubit state that I gave previously. Okay. Well, so either way, so you can either use this notation, this way of doing it, or this way of doing it, knowing that afterwards all you need to do is take these four components and put it into a 4D column vector. So that's for 2. We can do 3 between phi, psi, and chi. So where we have alpha 0, alpha 1, beta 0, beta 1, gamma 0, gamma 1. Likewise, so we know how to do the first 2. And for this, well, we do the same thing. So we take this one, multiply it by this vector, and then this one, multiplied by this vector, and so on and so forth. So we obtain 4 terms times 2 terms, 2D vector, which will give us our 8-dimensional vector. Okay. Again, we could multiply it in a standard way and developing and end up with the same result, but in a linear way. So what we see here is that the tensor product is something that basically multiplies the space at will between a twice 2D space into a 4D space. Okay, so what it means is that if I want to look at the circuit, the quantum equivalent circuit, then what I have is I can start with 2 qubits separately, and then I put them together in a calculation, so they don't have to be interacting in a sense that they don't have to be they don't have to have calculation on them, but in order to bring them together, so to increase the space to a 2-qubit space or a 4-dimensional space, then I use the tensor product. Okay, so now I've got these two, but now these two are a 4-dimensional vector rather than twice 2D dimensional vectors. And then I can carry on. Tensor product these 2-qubit state with the third one to have a 3-qubit state vector with 8 components, as we just saw, and so on and so forth. So, so this space, this qubit space that we've been talking about, that we can sort of multiply or increase, is what's called in math a Hilbert space. And there are a few things to remember. Is that a Hilbert space, it's a vector space, it's a linear with an inner product in the complex number field, as we saw. So there is an inner product with complex numbers. Hilbert space can be finite or can also be infinite. We won't see that much. We will only look into finite spaces, so finite number of qubits. And is also equipped with a norm, as we saw, when we can normalize all these vectors. And usually we do normalize this space into normalized vectors of 1. So just a summary, for 2D Hilbert space, we have these 2 components, 4D, these 4, and 8D, these 8, and so on and so forth. So again, we've seen that before, but the idea of parallelism, quantum parallelism, is that if I have one classical transistor, then I only have one outcome. It's either a 0 or 1. Transistor, either you press the button or you don't. If I have a qubit, I have 2 outcomes possible, because in a superposition state. 2 transistors would lead me to 2 outcomes, no matter what. It's linear. But 2 qubits will lead me to 4 outcomes, and so on, so forth. And excuse me. And as said before, if I were to have 51 qubits, that's around 2 to the power of 15 in terms of computational power. So it's sort of petascale computational power, and it's already the current computation power, the maximum computation power that we can do classically. So just with 51 qubits, although one issue is to have 50 very good qubits, whatever that means, but it's a very important point. But if we were to have 51 usable qubits in the perfect sense of it, then we would already beat any classical computer that use petascale computational power with many, many more bits of information. So that's what people are trying to do. So I covered here some examples of physical systems. So just a few examples. We'll come back to that. So those are companies and the technologies that they use. So we will see some of the technologies at a later stage. In particular, these two, the superconducting qubits using superconducting circuits. That's IBM, not just IBM, but IBM is one of them. There is, in the US, there's also the company called IonQ, which uses trapped ion. If you remember, I already discussed that people could trap single ion atoms in an optical and an electric trap, and then control that to actually make qubits. People look into also defects, electron spins in silicon and build a quantum computer out of this. So there's silicon quantum computing. It's based in Australia, I believe. And in France, there is also, for instance, a company called Pascal, which are trying to make qubits out of what we call neutral atom, as opposed to the trapped ions or the ions, which are charged atoms, and see how we can make a computer out of this. Those are just examples. I have no particular interest in these. I just want to give you some examples of companies that are actively working on trying to make a computer, quantum computer, out of different technologies. Right. So the very important notion of entanglement now. So we've talked about it before, very briefly. So entanglement, when you have a 2-qubit state, at least 2-qubit state, inherently you do have the notion of entanglement. So how do you do that? So let's go back to our 2 qubits, so psi and phi. Sorry, psi and phi. Let's tensor product them and have the 4 components, so A00 up to what I call D11. And of course, if we do this, then A, B, C, D are linked with alpha, beta, gamma, delta, because this is a particular factorizable state. But as soon as you move away from this particular case, for instance, as soon as you have this state, so B001 or plus C10, or this one, then basically any combination that is not this one is not a factorizable state. What it means is that the output state of the 2 qubits cannot be written as the product of the two, as in a standard sense, as a product of the 2 separate qubits. Okay. So, in fact, the definition of entangled state is a non-definition, in the sense that an entangled state is a non-factorizable state. So this, for instance, cannot be written as being the product of the qubit 0 and qubit 1. Okay. This is an entangled state that links together qubit 1 and qubit 2. And it cannot be factorized. So the notion of entanglement was actually originally a physical notion. It came from a very old debate in 1935 in this article by Einstein, Podolsky, and Rosen. So for the longest time, entanglement was called the Epr paradox, for Einstein, Podolsky, Rosen paradox. And what they found in this article is that they found that so quantum mechanics, as we will come back to it, can be explained. Any system can be defined in quantum mechanics by wave function. But what they found is that if you use two systems, then they realized that you could indeed find a wave function of the two systems that would be entangled. That would mean that the two systems cannot be separated. So what they found is that the wave function was non-separable. You could not separate the two entities, and yet you could have two quantum systems, physically separated. They realized that means that, or at least what they would claim is that it would mean that you have some instant correlation between two particles, two systems, no matter how far they are, and no matter how, despite the fact that nothing can go faster than light. So at the time, it was known that no information can be faster than light. And then they came up with other ideas, the fact that there has to be something hidden in space, some hidden variables that would explain the fact that these two particles know of each other and yet are separated. They are entangled. And that this global wave function would probably mean that quantum mechanics was, for them, the conclusion was quantum mechanics was not complete. There was something wrong. Okay. Turns out that there is, at least on this occasion, there is nothing wrong with it. It's just that entanglement is a quantum mechanical property that is counterintuitive and yet does exist. So they call it, just for the, so they call it a spooky action at a distance. Because again, what does it mean? Is that if I have a source of EPR particles, so at the time we called them PTS, so EPR particles. So if I have a source of, let's say, two entangled photons, we'll come back to that later on. I'll show you how in practice we can entangle two photons together. So, So if you were to take two entangled photons, and if you were to send one to Earth and then send the other one to the Moon, what they showed in this paper is under the right condition, under the entanglement property, these two photons, despite the fact that they are very far apart, do have a common property, do have a complementary property. And no matter what you do, if you do something on one, it kind of looks like you're changing the other one, and vice versa. And that's what was a big issue for them at the time in this article, saying that how can you modify something in one place when you do it in another place instantly? Okay. Well, it's a lot of almost philosophical debates on this. But at the end of the day, so the idea is not to go into the whole details. There's a lot of research and a lot of work going on onto this sort of EPR paradox. But what we can say is that if you see it as a global system, as a two-particle system being in fact one system, then there is no problem, first of all. And second of all, there is actually no correlation faster than light. Because when you have, we will come back to measurement, and that will be the next lecture. When you measure your photon on Earth, it doesn't actually do anything to the one on the Moon until you actually tell the other one on the Moon that you measured yours. What I'm trying to say here is that you do need some form of information between 1 and 2 to travel at a normal speed, or at least not faster than light, in order to actually say that you measured something. Or in other words, if you make your measurement, but keep it for yourself, then on the other side there is this information does not exist because you wouldn't know that something's been done on the other side. Anyway, so again, there's a lot of work. There's still a lot of work onto this, and how to implement that physically. So again, I will show you. I've been talking about photons, and I will show you specifically how we do this with photons using polarization states. Again, as we already saw. But for now, let's go back to sort of the mathematical aspect of entanglement. And in particular, these four states are very important. So those four states, so 2 qubit states, are called the Bell states, after John Stuart Bell. So he actually was the one who took the Epr paradox and kind of showed that there was nothing wrong with quantum mechanics. And in fact, the notion of this global wave function, and there's no hidden variables, no hidden people trying to trick you. And what you can show is that these four, so we recognize a 2 qubit state, so 0, 1, minus 1, 0, and 0, 1, plus, and so on and so forth. And these four Bell states are actually what we call maximally entangled states. Okay, so this is the maximum. You can actually define a degree of entanglement. And for 2 qubit state, these four Bell states are the maximally entangled states. They are not factorizable, as we said. We cannot write that, for instance, psi1 is the product of qubit 1 times qubit 2. Okay, where again qubit 1, so if it's 2 qubit is this one and qubit 2 is this one. And that the thing is, we can only, so what it says here is that it's not measurable, it's only locally. What it means here is that, but that's a good thing, because it means that despite the fact that there's an entanglement between these 2 qubits, so they have a common property, you can still do something on each of them. And of course, for quantum information, these do something on each of them means what? Means that we can apply quantum gates. We can apply a single qubit quantum gate on each of them, or as we will see, we can apply a 2 qubit quantum gate on both of them. Okay. And as I said, but I'll come back to that, this is actually extremely difficult to physically create, to physically have a system that is entangled. Okay, this is a big issue in order to do that. I'll show you in a minute how we can do it sort of simply with photons, but it's not easy. Yeah, and this is basically the so-called Bell experiment, so which is the same as pretty much the scheme that we have here, except that this is more of a experiment like where you would have a source of 2 particles that are entangled together, and then you measure each of them on each side by some device that will measure the 1-0 property of each. Okay, and depending on a series of measurements you can make, you can show that you have these maximally entangled state. Again, so experimentally, people do that on systems. So most of them is photons, but not just. Right. So how do we do that in practice? So there is actually a simple way, and for that we can come back to the experiment that was done by Young's double slit experiment. In fact, I brought it here. I'll show you how we do this. So the idea is the following: is you start with a light source. So I'm going to use a laser. And you send your light source onto a screen that has 2 slits or 2 holes. And you look at the results on the screen further. And what you would see, of course, depending on some parameters like the size of the holes and the distance between the holes, but let's say that all of this is, you've done what you're supposed to do in order to observe them. And what you should see is you should start to see interferences on the screen. And this is nothing particularly quantum. We would see the same thing with water. So those are actual images of water. So here's one slit where you can see the water making this kind of nice ring where actually the water wave is actually transformed into what we call a spherical wave. And we can see that if you have the equivalent of two slits, you can hardly see, but you can see that there is some interference effect. In other words, we can do that very experiment with water, no problem, or with sound wave. It's the same thing. And what we would obtain is, as I said, some kind of sinusoidal behavior on the screen. So that would be with light. So again, I'm going to show you in a minute. And typically what you can show is that the light intensity on the screen, so I, the light intensity I, would be the sum of the two intensities separately if you were to close each aperture one after the other. So you would have I1 and I2 for each aperture, plus this term, which is an interference term, where you have theta, where theta, so sine theta, where theta is what? Theta is basically the dephasing between the two waves from the two holes. So in other words, what it means is that you have to, again, realize that you have two waves. And if you look on the screen, you can see, so if I look on the left-hand side, you can see that this wave and this wave will not arrive at the same time, because one has to travel further than the first one. Even if they are at the same speed to start with, they will not arrive at the same time. And typically you would have a dephasing between the two waves. Okay, and this dephasing is given by this theta, and is what actually provides the constructive, as we call constructive and destructive interferences. Or in other words, we have the two waves, and sometimes they overlap to have a higher wave, or sometimes they compensate to have no wave. Okay, and that's what you would see again. So let me show you here. So I've got, so maybe if we can zoom in, Luca, thank you. So I've got a laser here. I'm going to put it on. So here's my screen, and here I have a plate with two slits. And what you can see here, you can see a succession of bright spots and dark spots. Okay, actually, what you can see is something like this, where you have this, and sorry, I should another one here, and this one a bit higher. And then it goes away eventually because you have what's called, and we see an example here, we have what's called a diffraction effect. But let's focus on the fact that you have indeed a succession of bright spot and dark spot due to these constructive and destructive interferences. And what I can do is I can, so I have here a razor blade, and I can try to block one slit and see what it does. So if I do it, here we go. So here, I don't know if you can see, but I basically still have light coming, but only from one slit, because I blocked the other one. And what I do have is no more interference effect, due to the fact that what I do here is I basically block one hole. And if I block one hole, then you can see, say, I2, then I2 goes to 0, then there is no more interference term. So all I have is light coming from one hole, or if I were to do it the other way, light coming from the other hole. But it's the combination of the two that will provide me with the interference term of constructive and destructive interferences. So you say, okay, so that's interesting, but so what? Well, actually, one way of seeing it is that, as we said, so this works for waves, but we said light is a wave, but light can also be described by photons. And what it means is that photons will actually do the same thing. Excuse me. So what does that mean, do the same thing? It means that if I take my laser and if I attenuate my laser down to, or a source of light, down to one photon at a time. So of course, one photon will not split into two. Okay, one photon cannot split into two. But what one photon can do, as we saw, is one photon can explore the two possibilities. So that means that on my screen, I will have, and I will show you a movie that's from a experiment where we see one photon at a time coming from the two slits. And of course, if you have one photon coming from the two slits, all you're going to see on your screen is just a spot where you detected the photon. But if you do it again and again and again, what you're going to see is successions of spots. But you will see after some time that these spots make sense in a sense that they give you this interference pattern the same way that you would have if you were to use the wave behavior of light. Okay. And so what does it mean? So well, let me show you first. So here is the screen. Oops, sorry, too fast. Here's the screen. And what you see is these white spots are photons detected on a screen. So each white spot is a photon detected. So when you have a few, there are 3, 5, 7, 8 here, well, it looks like it's random. One photon's there, one photon there. But then when you increase the number of events, then you see after some point that is not random, that there is indeed a pattern, that all the photons individually, they look like they impacted randomly, and in fact they did, but they randomly impacted in a given way, okay? Which is the equivalent of the interfering way between the two waves that light would provide if we were to send light. So you can see here, I'm going to show you the movie. So if I launch the movie, there we go. So you see here, it's the same thing as the left-hand side, but it's a real-time acquisition of the photons arriving on the detector. And you can see the impact of the photons on the detector detected on the screen. And so here is a 2D images, and here is just a sum of a whole pixel line. And you can see these interference pattern occurring. So it's a bit like this, like I told you, not just flat because of diffraction reason, but whatever. But the fact is, you can see these interferences after many, many occurrences. Okay. So what it means, so now if I go back to that, what it means is that a single photon has actually been through, can be seen as having gone through the two slits at the same time. And what I can do is I can now define a particular type of entanglement that we call path encoding. Okay? Because when I have a photon impacting on the screen, I don't know which hole it went through. But what I do know is that if it went through one hole, it hasn't gone through the other one, and vice versa. But as I don't know which one, I need to have the two in a superposition state. And that's where I can do a path encoding here. So this would be path encoding. excuse me, path encoding entanglement. Where I would define the wave function of the two slits as being, alors, I'm going to assume that the two holes, the two slits are equivalent, and that they are the same ones. Therefore, I would have 1 square root of 2, and the probability is the same. And now I can define a 2-qubit state being 0, 1, 1, 2, plus or minus, actually it depends, I put minus here, but it could be plus or minus, it depends on the spacing, on the phase, whatever, some numbers, it could, yeah. And then 1, 1, 0, 2. So what this notation means is that here I have some form of entanglement in the sense that if the photon has gone through slit 2, then I mean there is no photon through slit 1, so that could be my 0, 1 encoding. And vice versa, if it has gone through slit 1, then that means it has not gone through slit 2. Okay? So the fact that I can write 0 in 1 and 1 in 2, or 1 in 1 and 0 in 2, the fact that I can write it like this is an entangled state in path encoding. The entanglement is in path 1 and 2 now, where you can have an entanglement between the photon went this way and not there, or it went this way and not there. Okay. I can do that for 3 slits, so I can have three slits. Then, if a single photon is going through the 3 slits, then what I would have is, in a way, a 3 qubits state, because it's either the photon has gone through slit 1 and not the other 2, or it's gone through slit 2 and not the other 2, or it's gone to slit 3 and not the other 2. Okay. So this is what we can call path encoding entanglement, and is used quite a lot. I'll show you some examples. It's used quite a lot when using photon as qubits. Okay, I mentioned that photons, the polarization state of photons can be used as qubits, and I'll come back to that. But another way of using photons as qubits is to encode information onto the path that they take. Okay, and the good thing about that is that here are some examples. So some examples from companies like these two, but also examples from academic examples from universities. And what you have here is basically some integration, some integrated optics, where rather than having these slits here, that is not very useful, what you can have is an optical chip where you can have all these possibilities, all these paths. You remember I talked about beam splitters. I show you how a beam splitter can split the light into 2, or can split the photon path into 2. Well, if you now cram all these beam splitters and recombine them and so on and so forth, then you can do that on an optical chip. You have some examples here, and basically have this type of encoding, a path encoding, because now you have a circuit and the photon can go through this circuit, split and come back and recombine and so on, and have some very complex entanglement coding, entanglement path encoding into your optical circuits, and people use that to devise some small quantum algorithm or more developed quantum applications. Okay. In fact, I'll give you a good example. So this is from, so all of those are extracted from this website. And I like this because it's a nice illustration of this path encoding and the difference between classical and quantum behavior. So what you have here is what is called a Galton board. so you have a classical Galton board and you have a quantum Galton board. So a Galton board, we know that, we all use that or have seen that. It's something with pins here, and you just drop balls here, and then statistically, these balls will fall, and then every time the ball arrives on one pin, it has a 50% chance of going left or right. And if you do this, so if you then recollect the balls at the bottom with these 5 cups, then what you would find is, or if you have more of them, what you would find is what we classically have using a Galton board, which is a binomial distribution. So what it says is that the likelihood of having the balls coming down and arriving in the center is higher than on the side or much further on the side. Okay, so it's just standard classical probability distribution. Now, if you do the quantum version, what would be the quantum version is that instead of having each of these pins where the ball will fall from one side or the other, you replace these pins by these beam splitters. These beam splitters mean that, again, if you have a single photon, so here you can see the ball, the ball who is now a photon, that is actually can come out of these beam splitters in a probabilistic way, but in a superposed way. Okay, so in a superposition state of either I'm going to this side and not this side, or I'm going to this side and not this side. But both are possible because, again, that's what I showed you last time. If I send a single photon onto a beam splitter, okay, if this beam splitter is a separator of light with 50% chance of reflecting the light or transmitting the light, if the reflection is 50% chance and transmission is 50% chance, then if I have sort of a laser pointer with 1 milliwatt of power, as I said, then on average I will measure 0.5 milliwatt here and 0.5 milliwatt there. But when I have a single photon cannot split into 2, so the single photon will be either seen here or there, but in general it will be in a superposition state of being there and there. Okay? So that's what we see here, is that every time the photon or the probability of the photon arriving on the beam splitter, it will split into 2 at each beam splitter. And what it's going to do is that after some time, all these possibilities, all these path encoding entanglement will, like interferences, they will interfere, the path will interfere destructively, constructively, so that at the end, the result is completely different than the binomial distribution. Okay? This would be what you would have with the quantum Galton board, where you can see that, in fact, the probability to find the photons at the end, to detect it on these single photon detectors now, they're not just cups, is higher on the sides than in the middle. Okay? So this is a good example of a difference where between a classical, so in this case Galton board, and a quantum Galton board, where because of this path encoding and the fact that we can have a superposition of different possibilities, these can interfere destructively and constructively, and then end up with something that is completely different than what you would have in a classical system. And so this is what we call sometimes a quantum walk, the random walk. It's the same type of problem. And with the random walk, you find also some distribution like this. But in a quantum walk, you can actually have something that is, again, completely different than the binomial distribution. So you can do that. So people do that. So as I said, they can use an integrated circuit. So here's what you have here is two inputs. A and B. You have all the different outcomes here, which are detectors. And then in between, you have all these beam splitters. So it's the exact equivalent of that, except this is a cartoon, but this is an actual work. And you have some, what is called here, directional couplers. It's the other word for beam splitters, but in an integrated optical chip. And also phase shifters. Those are just things where you can change the phase, so you can actually change where your photon would be. So you can change the weight of each beam splitter, of each path, so that you can have a result, a different result depending on what you want. But the fact is, this experiment is how you would do this experimentally in the lab. Right. Okay. So again, let's do. So let's go back to what I call the physical meaning of psi. So again, some physics before we go back to math and computing. But I just want to come back to the fact that, as I said before, this bracket notation is not just a nice notation, and it's not just a mathematical object, because behind there has to be some physical system, so either photons or superconducting circuits or whatever, or electrons or spins, as we will see later on, that has a physical reality. And in fact, this is, so in quantum physics, if you take a quantum physics book, you will have the 5 postulates, the 5 postulates of quantum mechanics. And the first one tells you that whatever quantum system, S, or whatever particle, you can always define it by what we call a wave function. So like I said, a photon, an electron, you, me, we're all defined by an entity called a wave function. Of course, for us, it's not so important because we are a big object, so it's not what defines us the best. But at a single photon level, or at a single particle, electron, atoms, and so on, the wave function, the quantum mechanical wave function, has all these is very important to describe the system. So this function would be a function of space and time, and it can be represented in by what we call a quantum state vector, or a ket, as we saw, which we can write like this. This function is, without surprise, a complex function, usually. And then you will say, okay, but you said that, the wave function is supposed to represent physical reality, and complex is not a physical reality, and it's true. And that is because at the end, what we actually measure is not, or what we actually have access to in the real world is not the wave function, is the probability of finding the system at a position r in time t, say, in a small volume, given by the product of psi star times psi. So what we have is that we actually have the product of these two, which is now a real number. And this is what you measure. So if I want to find out where the particle is in that box, I will try to find the particle in the box. And that's, so with some probability, I will find it here or there or there. And that's what it gives me. It doesn't give me the wave function of the system. It gives me the property of the system, which is to have a probability of being at a position r at time t in the small volume. Of course, we have, no surprise, we have a normalization. So here the physical meaning of normalization is that if I integrate this probability density into the entire universe, then I find one. So in other words, what it means is that if I integrate, or if I look into the entire universe where if my particle is there or not, then of course I will find that it is there. I mean, this is the assumption that it has to be somewhere. So this is physically the normalization factor, is that if I look in the entire universe, I will find it with the certainty 1. So in practice, in 1D, so what this gives me is the so-called probability density function. And this would be psi star x times psi x over dx. So what it means here is that if I measure this quantity here, I will find the probability of finding my particle in between the distance x and the distance x plus dx. Okay. And so if I integrate over this length between x and x plus dx, then I have the probability of finding my particle in this interval of dx. So it means, again, that this bracket notation actually has a physical meaning, because, in fact, wave function in quantum mechanics are defined in a Hilbert space the same way as we said for the qubits. They are complex numbers, we already said. They have inner product. There's the inner product, so I can multiply wave functions together as long as I follow the inner product property, which is that the left-hand side and the right-hand side is not symmetrical. I've got to have a star on the left-hand side. And that there's a correspondence between the right-hand side ket notation and the left-hand side bra notation. So that when I, for instance, normalize to 1, then I take the integral of the entire psi star psi, that's 1. And if I translate that into the bracket notation, I end up with my bracket inner product between psi and psi in this particular case. So it's normally the norm of the ket psi. And this would be the generalization of having a psi phi product of the inner product. Okay. So remember, I did tell you that mathematically there is a direct correspondence between this bracket mathematical notation and this notion of dual space and so on, the column vectors and the line vectors. But there is a direct equivalence with these this integral and these wave function systems that can be manipulated the same way. And then afterwards, well, once you're in the bracket notation, then you can use all the properties that we've seen before with bra and kets, because what you know now is that what's actually behind this is a physical meaning of, in this particular case, having the integral of psi star psi over a volume dV. But now I don't need to manipulate those anymore. I don't need to manipulate integrals and so on. I can just manipulate bracket even to describe physical systems. And in fact, that's what we're going to do to describe, for instance, the spin of an electron. And just to give you a preview, we'll come back to that, or in particular to what's called the Schrodinger Equation. So this is, as you know, the Newton's law sorry, not in quantum mechanics, in classical mechanics. So this is what we use to explain classical mechanics. And the counterpart in quantum mechanics, so we'll come back to that, but much later on, is the so-called Schrodinger's equation. And Schrodinger's equation is basically an equation that tells you how this object, this system, will behave as a function of time. And so this wave function will behave as a function of time. So it can be written in terms of function, or it can be written in terms of ket notation as well. The difference now is that if you do this, then this quantity here that is called h, in this case, it can be seen as a measurement. In this case here, it can be seen as what we'll see as an operator or as a matrix. In fact, so in quantum mechanics, I mean, this H is an operator, and what it is what we call it the Hamiltonian for H. And what it is the total mechanical energy of the system. And the total mechanical energy of the system is the sum of two energy. It's the sum of the kinetic energy and the sum of the potential energy. And these two provide the total energy of the system. And in quantum mechanics, Schrodinger's equation basically tells you that if I know the total energy of the system, I know exactly what's going to happen to my system. So I know exactly through Schrodinger's equation how my wave function is going to be transformed or changed as a function of time. So that's the physical meaning. If I want to translate that into quantum information, into qubits, then I have the same thing. In a sense that I would go from this qubit to this qubit through this, operation, this single qubit quantum gate. We'll come back to that later. The Pauli, you remember, we've seen the Pauli matrix. So I can transform psi into psi prime and psi prime into psi second. But those x and z and y and so on are in fact, physically, operators, the same way as here, as this Hamiltonian, that physically transform your system into another system. Or in this case, your qubit into a different qubit. And then from that, then you can just leave the physics behind, underneath, underlying, and just as we will see later on, then make quantum circuits where you would have, say, a 3-qubit circuit here. So 1 qubit, 2 qubit, 3 qubits. And in this particular circuit, what you have here is what we call a quantum teleportation circuit, where you would teleport this qubit onto this qubit here. So you would physically move 1 qubit and teleport it to another one. So we'll come back to that later on. But I just wanted to say that there is a physical meaning behind that we should be aware of it, but that for doing quantum technologies, like I said before, it's like classical computers. Most of us use computers now, and we don't actually know, or we don't know exactly how transistors and all of this actually work behind, but we don't actually care because now we are at a level we don't need to know that. Right now for quantum technologies it's not the case, so we still need to remember that there is a physical meaning behind and a lot of work to do on that. But if we want to focus on the quantum information part, then we can just leave the physics behind underneath. Right. Okay. So this is it for lecture 4. So now I just talked about the notion of operators, and I will now explain what. So the link between the physical, again, the physics part. So the operators and measurements, and how it links to the next lecture, which will be to actually make quantum gates. So here is the program. So first, again, some physics. It's a lot of physics today, but later on there will be less physics when we'll go on to quantum gates and quantum algorithm. So the first one is a bit mixed. It's about the notion of operators in quantum mechanics. It's a bit mixed because we will see that there's also a lot of mathematics behind at the end. We're talking about matrices. Then, as promised, I will focus on a particular system, another physical system, which is the spin state of an electron. So I will keep it low profile, but just to introduce it because it's a nice alternative to photons to illustrate some aspects of quantum technologies. And then I will move on to measurements, what it means in physics to make measurements, and in particular the notion of the collapse of the wave function. So that's a very important notion in quantum physics, but it's also a very important notion in quantum technologies, because the collapse of the wave function in quantum technologies is basically means that you measure, you move from having a quantum system to a classical system, which is your result. And then I will talk about the notion of mean value of an operator, because operators are actually, so they are mathematical objects representing physical measurement. Say you want to measure the electric field somewhere, you want to measure the spin of the electron, so you actually make a measurement, and you can define a mean value. And also the very important notion of commutation. And the very important notion of commutation is important because, well, as we saw already, the fact that we have this dissymmetry between the left-hand side and the right-hand side means that we cannot have commutation necessarily when we do certain operations, or when we do certain gates, quantum gates, for instance. We will see the order matters. The order you do it is important. And then I will finish with, for this part, so not today, we won't do all of this today, but I will finish with the last kind of mathematical object that we need, which is the notion of outer product. Okay, so we've seen inner product, tensor product, and now we're going to see outer product. Right. So I talked about the first postulate of quantum mechanics, so let's go back a bit in physical system. But there is the second postulate. And the second postulate is to tell you what I already said, is that for every observable in classical mechanics, or in classical physics, I should say, so anything that you can measure, a current or a magnetic field or voltage, anything, in quantum mechanics you can associate what we call an operator to it, which have to have some properties. First of all, it's linear, and second of all, it has emission properties. Emission properties. So we've seen it before, and I told you that the matrices that we're going to need for the brackets have to have this emission property. And that's because we see now a bit more why, because behind there is a physical meaning, because it's a measurement of a current, or the measurement of a charge, or measurement of the position x. So the position of a particle. So classically, I just measure x. Well, the quantum mechanical version is if you remember, this hat here on top of it, is I told you that this has a meaning, is because now this is the operator measuring the position x. Okay, it's the quantum mechanical version of the classical physics. So I can do that for various quantities. So I can do it for the momentum. So the momentum in classical mechanics is the mass times speed, but usually we prefer the momentum version p, which in quantum mechanics is given by the operator p of x, if it's the momentum along the x direction. The total energy, so we call it the mechanical energy in classical physics. Here we just saw that we can define an operator that we usually call H for Hamiltonian. So H for the Hamiltonian of the system, which once we know it, can give us all the information we need for thanks to Schrodinger's equation to define your system. And then other operators like an angular momentum. So in physics we can have angular momentum, and we will see an example of the spin of an electron. So we can define an operator associated to it. L, most of the time it's called L with the hat. The same for the spin of an electron. S, well, we can define the operator associated to this property, which is S hat of Z. We'll see why it's Z for the spin measurement. So all these operators, which are the representation quantum mechanically, the observable, the so-called observables or the operators of the observables of these quantities, have to be, like I said, linear and Hermitian. Hermitian means that each of these operators have to follow these properties, where we have a hat equals a hat dagger, where dagger, remember, is the complex conjugate and transpose. So once we have this, then once we have these operators, so those operators are actually matrices in the bracket formalism. So it means that what I have here is linear algebra, because now, so for the, say, psi, so the ket psi, we said, so the qubit can be written alpha 0 plus beta 1. And we said it's a column vector, which means that if I want to go from one qubit to another one, I can use transformation. I can do an operation on it, and this transformation would be using a matrix. So in this case, is a 2 by 2 matrix. So it has to be something like this, A, B, C, D, with the particular property that has to be equal to A dagger. And if I do this, now these A's are actually operators that are linked to observables again. So something that I can measure. So if it's something that I can measure, that means I will have specific results. So how do I find these results? Well, I use linear algebra. So classically, linear algebra tells you that I can, for a given matrix, I can find out the so-called eigenvalues of the matrix and the eigenvectors associated to these eigenvalues. So for the French speakers, I put the translation of eigenvalues, eigenvectors, so valeur propre and vector propre, because they're very far from being the equivalent of what we have in English. And so what you would do is you would take, so in sort of a classical algebra, you would define, you would look into your matrix, find out what are the eigenvectors and the eigenvalues of your matrix. Here is the same thing, except that now we have operators, okay, and we have column vectors kets, and we would have eigenvalues that can be complex numbers. Okay. But this is the equivalent of what I would have here. Except that now, physically what it means is that this is the operator, so it's a physical measurement I'm going to make. This is the state of my system, which can change after I make the measurement. And this is the result of the measurement. In fact, this should be this squared is the result of my measurement. So how do we find V and lambda? Well, I can use the classical way of finding in linear algebra to find the determinant of AV minus lambda V. And I would find the eigenvalues and the eigenvectors, except that now these eigenvalues and these eigenvectors, so eigenvectors, have a physical meaning, which is that the eigenvalues are the possible result of the measurement, potentially what I'm going to measure, and the eigenvectors are the possible states of the system after my measurement. Okay. I'll give an example later on to see how to picture this. So, well, let's have a look. So, how we would do this in practice. So let's assume that I have an operator that looks like this. So I've got this matrix, which again in physical world is an observable. And then so I've got this. The numbers. The first thing I need to check is whether A equals to A diagram. And that is the case, because if I take the complex conjugate of that, I will transform the plus into minus and the minus into plus. And then if I transpose, I will put the minus back here and the plus down here, and I end up with the A. Okay, so I'll let you do this, but this is okay. And then I can find out, so what are the eigenvalues and the eigenvectors of my system. So what I'm going to have is something like this, where I have 2 minus, so if I define V, the column vector, the ket, with V1, V2, which can be complex numbers, then typically what I'm going to have is 2. Let's write it first. So A V is going to be 2 V1 plus 3 1 minus I V2. And the second one is going to be 3 1 plus I V1 plus 5 V2. Okay. So that V1, V2 are the components of my eigenvectors that I'm searching. So if I carry on again, this is standard linear algebra. Then the determinant, then the determinant of A V minus lambda V is going to be, I'm going to have, I'm not going to do it all anyway, but lambda v, so it's simply lambda v1, lambda v2. So if I calculate the determinant of this minus this, then I can show, I'll let you do this, that you're going to find two eigenvalues. The two eigenvalues will be 8 and minus 1. Once I've got these eigenvalues, I can determine the eigenvectors for each of them, the two eigenvectors. There is an infinity of eigenvectors in terms of proportionally, but 2 are enough as long as they are orthogonal with each other. So these two, for instance, work. If I take A1 equals 1 and 1 plus I, I took A1 and A2 rather than V1, V2, same thing. 1 and 1 plus I and 1 minus I and minus 1. So these, I should have called them V1, V2, really, it doesn't matter. So 1 plus I and 1 minus I minus 1. Those should be orthogonal states, orthogonal vectors, and they are, because if I do V2, V1, remember the bracket version, so that means I have to take the bra of diskette. So the bra of diskette is transpose and then complex conjugate. So the V2 is going to be 1 plus I minus 1, and the V1 doesn't change, so it's 1 plus I. Excuse me. And so if I multiply this, I have 1 plus I 1 plus minus 1, 1 plus I. And this is going to give me 0. So I do have indeed orthogonal states. Here, in fact, I took the other one, but it's the same thing. So, in other words, again, what we said is that these operators, so A, as long as they are emission, they can potentially represent what we call an observable. They can potentially represent a measurement that we make on our system. And for emission matrices, the eigenvalues are actually real values, because again, like I said, when you make a measurement, you don't measure a complex current or complex magnetic field, you measure a real value in the physical world. Right. So that's what I wanted to say on that. So let's introduce now the second physical system that we're going to use, and especially to illustrate these aspects. And in particular, I want to talk about a property of electrons. So electrons are negatively charged particles, and they have a proper inherently specific property that we call a spin. So before that, let me go back to the notion of angular momentum. So if you take a spinner and if you spin it, you can define what we call an angular momentum. So if you have something that is spinning like this, you can define angular momentum L as being the scalar product between the distance to the center times the speed of rotation. Sorry, vector product with the speed of the rotation. In fact, the angular momentum is the so the distance to the center, and then cross product with the momentum p, which in classical physics is mv. So if I write this, so if I have something that is spinning, something that is a mass m with a radius r, then when it spins, so it will have a certain speed, v, rotation speed. Then I can define something that is going off the spinner, which is called the angular momentum L, as being the cross product between r and n times v, or in other words, r and p. So sometimes the angular momentum is also written m. So a way of seeing it, for instance, the Earth orbiting around the Sun would be the angular momentum equivalent of that for the Earth around the Sun. But now, electrons in particular have another spinning property, which is again intrinsic to them, is what we call their spin state. And so this angular momentum here could be seen as the electron precesses around the nucleus, the same way. This is wrong, but this is a nice view of seeing it. In practice, it doesn't actually look like that, but again, it's a nice view of seeing it. So you can see the electron precessing around the nucleus, like Earth around the Sun. But then the electron itself can precess, can spin along as it goes around the nucleus. So again, like the Earth is rotating night and day along the Earth axis as it's going around the Sun. So this behavior would be the equivalent of the spin of the electron, except that this spin state property is not continuous as opposed to the Earth spinning on itself. It can only have two typical states. So in other words, it means that the electrons can only precess in one direction or the other direction. And if it does, so we can implement, so if that's the case, so we can define so if it's a precession like this, we define an angular momentum going upwards, or if it's precessed the other way, an angular momentum going downwards. And that's the spin up state, and that's the spin down state. And that's it. An electron, so we define it by mu, the spin of the electron. So this is the classical equivalent. So mu would be some number gamma times vector s, where s is the spin vector. So mu is the spin magnetic moment, because the spin of an electron is actually sensitive to magnetic field. So in a way, we can see it. We can see that electron spin as being a small magnet, where you have a north pole and a south pole. Anyway, if you say, okay, whatever, this is physics to me, then you say, all I'm interested in is what are the two possible states? Well, the two possible states are given by a plus spin or minus spin, and the values are actually given by h bar over 2 or minus h bar over 2. And that we see again the very important characteristic, the so-called Planck constant, h or h bar. Again, h bar is h over 2 pi. This is the equivalent. So the Planck constant which actually has actually the units of a angular momentum. Okay. So the spin of an electron is a form of angular momentum. Therefore, the units will be units of h bar. Except that now, like I said, typically the two values of the spin is only spin up or spin down. So 1 or 2. Again, this could be our qubit, this could be the state 0, this could be the state 1. So the two eigenvalues in this particular case, the two results, so if I were to measure the spin, I would either find a plus h bar over 2 or minus h bar over 2. So if I want to write that, that in a matrix way, if I have, so let's write it. So if I have so spin of an electron has two states. So we usually call it up for processing upwards, down for processing downwards, or spinning rather than processing, spinning, sorry. And the actual quantity is plus h bar over 2, so that's why also we put it, we associate it to the up version, and minus h bar over 2. So if I want to look at the operator, the spin operator, so the physical object that quantum mechanics will use as a representation of the spin, then I will call it Sz. So we'll see why z, and I can write it as being a 2 by 2 matrix because I only have it's a 1 qubit space where this could be, say, 0 and this could be 1. So it's a 1 by 2 matrix, and the 2 by 2 matrix, well, the eigenvalues matrix will simply be minus h bar over 2, 0, 0, sorry, plus, and minus h bar over 2. So why z? Well, because if I factorize it, then what I have is something like this. And this is the Pauli matrix Z, or sigma 3, that we defined some time ago. So that's why we call it Z. And usually that means also that implicitly the spinning axis of the electron is taken to be along Z. So this operator is the spin operator. So physically, if I measure the spin of my electron, I will find either this value or this value. And this can be is in fact the Z matrix that can be applied to a qubit 0, 1. So what about the other two? We have we'll see that. So we can define, the two spin states, so plus h bar over 2 minus h bar over 2. So like I said, is the sigma 3 that we define as an example of the Pauli matrices. For each of these eigenvalues, I can associate eigenvectors. So they would be the state, so the electron is in the state up or is in the state down, which would be the 0 or the 1. So that means that if I apply Sz to up, I will find h bar over 2 up, because up would be something like this. So let's write it. Okay. So the eigenvalues, I didn't write them. So those so these are the eigenvalues. So plus minus h bar over 2. And I can associate eigenvectors. Eigenvectors. So up and down, say, which would be the 0 and 1. Okay. And so if I apply Sz to up, that means Sz to 0, which is Sz to 1, 0. Then what I have is the multiplication of this times this column vector, and that would give me h bar over 2, 1, 0. So h bar over 2 up. Okay. And same thing for down. If I apply Sz to down, I will end up with minus h bar over 2 down. Okay. So it's the equivalent, again, in linear algebra, as the matrix times vector v equals, so eigenvectors, eigenvalues, and eigenvectors. So in other words, what it means is that I can define the wave function or the qubit function of my electron spin. And what would be the most general notation for that? Well, my electron could be in any state, any superposition state of being up or down for the spin. So that means that alpha up plus beta down is the most general way I could define the spin state of my electron. And that is precisely a qubit state. Now again, if I replace this one by 0, and if I replace this one by 1, then it's my qubit state. But now I physically imprint that on of the electron, which is the spinning property up or down of the electron. And again, the most general way, if you have no particular reason to put your spin in one way or the other, then alpha and beta are most likely equiprobable. So that means that you would have the most 50% chance of being in the up state, or 50% chance of being in the down state, and 1 over square root of 2 squared. Right. So now let's go a bit further for today into the notion of measurements and the notion of the collapse or the wave function collapse. So what is a measurement? So in quantum mechanics, a measurement is you take your quantum system. So this would be in the most general way. So if we're talking about the spin of an electron, then it's alpha up plus beta down. And then you make a measurement. So this is a measurement apparatus. So what it means is that you measure what the spin of your electron. And of course, you are not going to find that the spin of your electron is in one state or the other, because this is quantum mechanical state. You're going to measure a physically classical measurement, a classical result. Again, I go back to the idea that if you try to find whether an electron has gone through a small tunnel through a small barrier or not, then you will find the electron either one way or the other, but not both. Okay, so you will, same for the photons. If the photon has gone one way or the other, at the end of the day, on your screen, the photon is in one place. It has been measured. So once you made a measurement, you started with something that is equiprobable, but then you end up with only one result. So it's either up or down. So what you do here is what we say, you took the wave function and you collapsed it. Collapsed it means that you forced, or you put it in a way that you cannot have the two possibilities anymore, that you made the wave function you forced it to have an output. So either you find this result or you find this result. Okay. So you could say, well, then we are done. We are then this is not interesting for a quantum computer. But you're right, because the quantum computation power is done before these measurements. And that's where it's hard, is that you must do some operations, so you must make some gates, so 1 qubit gates or 2 qubit gates. So preserve that before in order to do your computation. And then at the end, because at the end you need a physical result, then you will measure and find an output. But once it's done, and that's also very important properties of quantum mechanics, is once you collapsed your system, so once you measure this result, then this is it. If you measure it again, you will find the same thing, because you force the system to collapse into one property and not the other one. And it cannot go back unless you have to do something. Okay? But once you measured, this is it, you change your system, you destroyed your qubit, you destroyed your superposition. And that's also a very quantum behavior that we don't have classically, is that classically, if you measure, if you look at something, you do not change, if you measure something, you do not change the something. If you measure the current in a circuit, you do not change your circuit. If you measure it again, you will find the same current. Here, in your quantum mechanical system, once you measured your qubit, once the measurement is done, you forced it to be in one result, and this is over. This is over. This is it. The measurement is done, and there is no way back to do that. Okay, so how do we do this? So again, we can define operators to do that, and in fact, what they are projectors. So this is the up projector. So we call it like this, and we'll see later on. This notation is the outer product. I told you we're going to talk about this. So this would be the projection along the up state, and this would be the projection along the down state. And indeed, if I apply this operator here onto my psi, I will find this result. And if I apply this projector, so the down projector, onto my psi, I will find this result. Okay, so let's have a look. Put that here, and then we'll stop at that. Let's have a look quickly. Up. So I define the projector along up being something like this. So ket bra. Oops, sorry, up. And I apply this to my wave function, which is the most general way of being in superposition, up and down. So if I do this, I've got up onto alpha up plus beta down. So that means this times this plus this times this. Alpha and beta are numbers, so I can take them out. So that means I have alpha ket up, bra up, and then ket up again, plus beta ket up, bra and then ket down. But if I isolate this is just the inner product between up and up, and the inner product is a normalized quantity of a vector, and that would be 1. Okay, because all the states, we have normalization, so up, these eigenvectors will be normalized, down. And then here, I've got the inner product between the bra up and the ket down. But those eigenvectors, and those again are the eigenvectors of the spin operators, are orthogonal vectors. So that means that this is 0. Okay, so this is 0 because they are eigenvectors. And I end up with alpha up. So indeed, you can see that applying this operator, this projector operator, I went from this general state to a specific state, which is being in the up spin. If I apply the other projector down, I will find the down result. It's the equivalent again, and we saw it, to the projection I would do if I were to have a vector psi, and if I want to know the projection of psi along x or along y, I would find psi x and psi y, and this is exactly the same thing. This is the projection operator of projecting this vector along y and x. Here it would be along up and down. But at the end, you saw that we see that we go from a superposition state to a single outcome, which is in this case being in the up state. So we say that we collapsed the wave function. So we forced the wave function to at the end be in more closer to a classical system where we only have one possibility. Right, so I'll come back to that next week. So we'll finish this lecture and then start onto at some point onto the notion of quantum gates. So with that, thank you, and I'll see you next week.